Imagine looking up at the moon, our constant companion, quietly orbiting above. But what if, for just a split second, you saw a tiny spark on its surface, a brief, brilliant flash against the darkness? This isn't science fiction, it's a real phenomenon, a meteoroid slamming into the moon at cosmic speeds. Unlike Earth, the moon has no atmosphere to burn up these space rocks. Every impact hits with full force. The result? An explosion so intense it vaporizes rock and soil, creating a flash visible from Earth. These flashes are rare to catch, not because they're uncommon, but because they're so brief, less than a tenth of a second. Scientists estimate several visible impacts happen each year, but spotting one requires perfect timing and equipment. You can only see these flashes on the moon's night side, where the darkness makes them stand out. On December 14, 2024, astronomers captured one of these flashes live, a direct observation of a cosmic collision. It wasn't just a discovery in old data, it was a real-time event unfolding before our eyes. This fleeting spark is a reminder. The solar system is a dynamic, sometimes violent place. The moon, lacking an atmosphere, serves as a giant witness plate, recording every hit over billions of years. Each flash is a tiny temporary star, a cosmic event that connects us to the ongoing story of our solar system. The moon's battered surface is a testament to these countless impacts. Every spark we see is a clue to the forces shaping our cosmic neighborhood. The next time you look up, remember, the moon is alive with activity, even if it's just for a moment. How do you catch a cosmic bullet in action? It takes patience, precision, and a bit of luck. The December 2024 flash was spotted by astronomers using a network of telescopes aimed at the moon's dark side. These telescopes, equipped with sensitive cameras, record the lunar surface non-stop, waiting for a fleeting flicker. The timing was perfect. The Geminid meteor shower was at its peak, and the moon's crescent phase provided a dark backdrop. Clear skies sealed the deal. Suddenly, a single pixel on the monitor flared to life, a flash in the Mare Frigoris, gone in an instant. Automated software flagged the event, and a second telescope hundreds of kilometers away confirmed it. This real-time confirmation made it a powerful discovery. In the past, we studied craters after the fact. Now, we witness impacts as they happen. Measuring the flash's brightness and duration gives scientists clues about the object's size, speed, and energy. Each live observation is a window into the dynamic processes shaping our solar system. It's cosmic forensics, unfolding in real time. What caused this brilliant lunar flash? The timing points to the Geminid meteor shower. As Earth and the Moon pass through the Geminids' debris, tiny particles burn up in our atmosphere. But on the Moon, they strike the surface. Scientists estimate the impactor was about the size of a grapefruit, weighing around 40 kilograms. Traveling at 35 kilometers per second, even a small rock packs a massive punch. The impact created a crater about 3 meters wide, releasing energy equal to 100 kilograms of TNT. The flash was visible from Earth, evidence of the violence of even minor cosmic collisions. Linking this impact to the Geminids helps us map the distribution of debris in our solar system. Each event refines our understanding of the hazards in our cosmic neighborhood. Lunar flashes are more than cosmic fireworks, they're vital data points for planetary science. By counting flashes, we measure how often the moon gets hit today, not just in the distant past. This real-time data calibrates our models of crater formation and solar system history. The brightness of each flash reveals the impactor's size and energy, helping us build a census of small, hard-to-detect objects. The moon acts as a giant detector, lighting up with every cosmic bullet it intercepts. These observations reveal how space weathering shapes planetary surfaces. Each flash is a piece of the puzzle, showing how our solar system evolves. As we plan to return to the moon, understanding lunar impacts becomes a matter of safety. Even tiny meteoroids can threaten astronauts, habitats, and equipment. Data from impact flashes helps engineers design shielding and plan for risks. Every flash is a warning. The moon is an active environment, and we must prepare for it. For future explorers, this information could be as vital as a weather forecast. Advances in technology have made real-time lunar impact detection possible. Sensitive cameras and automated software scan terabytes of footage, flagging split-second flashes. Multiple telescopes confirm genuine impacts, ruling out false positives. Spectrographs can analyze the flash's light, revealing the composition of the impactor and lunar soil. Future telescopes and lunar seismometers will make these observations even more powerful. Combining light and seismic data will revolutionize our understanding of impacts. Technology turns the moon into a laboratory for cosmic forensics. Each new tool brings us closer to decoding the moon's ongoing story. Each lunar impact flash adds to the story of our solar system's evolution. The moon's surface is a historical archive, recording billions of years of impacts. Studying both ancient craters and modern flashes helps us understand the environment Earth travels through. These observations refine our models of near-Earth objects and planetary defense. Systematic monitoring turns the moon into a giant particle detector, informing all of planetary science. The next time you look up, see the moon as a dynamic world, alive with cosmic history. Each flash is a message from the universe, telling us where we've been and where we're going.